The original question pertains to whether the code stipulates a supplemental earth ground for each light pole, including its required size. However, based on the information given, the code does not explicitly mandate a supplemental earth ground for every light pole. This is a crucial distinction because electrical codes are very specific in what they require. If a specific provision isn't stated, it's generally not a requirement. However, this absence of a specific mandate does not negate the need for proper grounding practices for light poles. Grounding is essential for electrical safety, protecting people and equipment from electrical shock and damage. Grounding provides a low impedance path for fault current to return to the source, enabling overcurrent protective devices like circuit breakers and fuses to quickly interrupt the circuit during a fault condition. This rapid interruption minimizes the duration of the fault, reducing the risk of electrical hazards. The National Electrical Code, or NEC, does outline general grounding requirements that may apply to light poles, even if a supplemental earth ground isn't explicitly required. It is essential to review Article 250.4 of the NEC, which covers general requirements for grounding and bonding. Proper bonding ensures electrical continuity and conductivity, maintaining a low impedance path for fault current. This is achieved by connecting all non-current carrying metal parts of the electrical system, including light poles, enclosures, and equipment, to the grounding electrode system. The size of the grounding conductor in the grounding electrode system must comply with NEC tables such as 250.66 and 250.122, which vary based on the size of the overcurrent protective device protecting the circuit. While a specific supplemental grounding electrode may not be required, there are several scenarios where it would be prudent or even necessary to install one. Firstly, local soil conditions play a significant role. If the soil resistivity is high, it may be challenging to achieve an adequately low grounding impedance using only the building's grounding electrode system. High soil resistivity impedes the flow of current into the earth, reducing the effectiveness of the grounding system. In such cases, a supplemental grounding electrode can help lower the overall grounding impedance and improve the effectiveness of the grounding system. Secondly, the distance between the light pole and the building's grounding electrode system is a factor. If the light pole is located far from the building, the impedance of the grounding conductor may be too high to provide effective grounding. The longer the grounding conductor, the higher its impedance, which can limit the flow of fault current. A supplemental grounding electrode located near the light pole can minimize the length of the grounding conductor and improve grounding effectiveness. Thirdly, specific project specifications sometimes dictate the need for a supplemental ground. Project engineers or designers may include supplemental grounding requirements to enhance safety or meet specific performance criteria. It is crucial to carefully review project specifications and drawings to identify any supplemental grounding requirements. Now, let's consider the methods to implement a supplemental grounding electrode. Firstly, ground rods are a common choice. These are typically copper-clad steel rods driven vertically into the ground. The NEC specifies the minimum size and length of ground rods, typically 8 feet in length and ranging from 1/2 inch to 5/8 inch in diameter. Multiple ground rods can be installed and spaced at least 6 feet apart to further reduce grounding impedance. Secondly, ground plates are another option. These are metal plates buried in the ground, providing a larger surface area for contact with the earth. Ground plates are typically made of copper or galvanized steel and must meet minimum size requirements specified in the NEC. Thirdly, ground rings can also be used. These are bare copper conductors encircling a building or structure, buried directly in the earth. Ground rings provide a continuous grounding path and can be particularly effective in areas with poor soil conditions. Regardless of the method used, the grounding electrode must be properly connected to the light pole's grounding system. This connection is typically made using a listed grounding connector and a grounding electrode conductor size according to NEC Table 250.66. It's also important to consider the potential for corrosion of the grounding electrode and connections. Corrosion can increase the impedance of the grounding system and reduce its effectiveness. Using corrosion-resistant materials and proper installation techniques can help minimize the risk of corrosion. Here are some best practices for light pole grounding. Firstly, always consult with a qualified electrical engineer or contractor. Grounding system design and installation require specialized knowledge and experience. A qualified professional can assess the specific site conditions and design a grounding system that meets all applicable code requirements. Secondly, conduct soil resistivity testing. This testing measures the resistance of the soil to the flow of electrical current. The results of this testing can be used to determine the appropriate type and size of grounding electrode needed to achieve an adequately low grounding impedance. Thirdly, use listed grounding components. Listed components have been tested and certified to meet applicable safety standards. Using listed components ensures that the grounding system will perform as intended and provide adequate protection. Fourthly, inspect and test the grounding system regularly. Grounding systems can degrade over time due to corrosion, damage, or other factors. Regular inspection and testing can identify any problems early on and allow for corrective action to be taken. The effectiveness of the grounding system should be tested using a ground resistance meter. This meter measures the resistance between the grounding electrode and remote earth. The measured resistance should be below a certain threshold, typically 25 ohms or less, as specified by the NEC. Fifthly, document the grounding system. Keeping accurate records of the grounding system design, installation, and testing can be helpful for future maintenance and troubleshooting. This documentation should include the location of all grounding electrodes, the size and type of grounding conductors, and the results of any soil resistivity testing or ground resistance measurements. It is important to note that local codes or regulations may impose additional requirements for light pole grounding beyond those specified in the NEC. It is essential to check with the local electrical inspector or authority having jurisdiction to ensure compliance with all applicable requirements. Failure to properly ground light poles can have serious consequences, including electrical shock, equipment damage, and fire hazards. Proper grounding is an essential safety measure that protects people and property from electrical hazards. In summary, while the code does not explicitly require a supplemental earth ground for each light pole, proper grounding practices are essential for electrical safety. Factors such as soil conditions, distance from the building, and project specifications may necessitate the installation of a supplemental grounding electrode. Always consult with a qualified electrical professional and comply with all applicable codes and regulations to ensure the safety and reliability of the electrical system.